Good day and welcome to the culminating point of chapter 2. So we're going to talk about the ideal gas law. Before I show you the math behind the gas law, we're going to talk about a few theoretical points. So first of all, obviously we've said before that perfect gases don't exist, but we need some kind of reference point to compare our results to. So we always compare our results to an ideal hypothetical gas. But in reality, this gas does not exist, right? Now, in your textbook, they talk about, they compare a hypothetical ideal gas to a real one. I'm going to go very quickly over this just to explain the statements. It's not that they're not important, but they're not critical, and some of them, quite honestly, I don't know how they even compare to each other, but hey, listen, we'll go over them anyways. So, for the first one, we know that particles of a gas are infinitely small, right? And their size is negligible compared to the volume of the container that holds that gas. For a real gas, we say that when the pressure is high, the particles move much closer together, obviously because they move faster, so there's more collision, so it kind of tends to make them move closer. And because of that, their size becomes very important. The bigger the particles, if they're going to be closer together, there's going to be more interaction, so they're not going to behave perfectly at that point. So the size becomes important for a real gas, especially at high pressure. For hypothesis number 2, the particles of a gas are in constant motion and they move in straight lines, so we know this already. Versus a real gas, when the particles of a real gas collide, they lose a little energy. So the energy is not constant. The collisions are not what we call elastic, whereby even if there's a collision, there's no exchange of energy. That would be for a hypothetical or ideal gas. When two particles collide together, they each go their way and nothing loses energy. The energy stays the same, the speed stays the same, everything stays even. For a real gas, it's not the case. When two particles collide together, there is an exchange of energy. One may slow down, one may accelerate a little bit, so it's not perfect. Again, those collisions are not exactly elastic. So that means that it influences also the pressure, because if the speed is not going to be the same, the collisions won't be all equal, and if collisions happen at a slower pace or speed, there's not as much energy involved, and therefore the collisions are not as efficient, not creating as much pressure in a sense. So the pressure may vary a little bit with a real gas. As the particles collide, some particles become weaker or they start traveling more slowly, and therefore the pressure exerted through those collisions is not quite the same. So it's not perfect. For hypothesis number 3, the particles of a gas do not exert any force of attraction or repulsion, so no attraction or repulsion, no interaction between them, as opposed to a real gas. As the temperature decreases, the particles slow down, right? That we know, that makes sense. At a given temperature, the particles attract each other, so there is some kind of attraction, or there can be repulsion as well. So there is some kind of interaction between the particles of a real gas. So that again may influence the number of collisions that occur. It may also you have to take into consideration that when they collide, because of those attractions, some of them may slow down. The exchange of energy may be different than for an ideal gas, etc., etc. So there is some kind of interaction which we have to take into account when we look at the collisions and therefore the pressure exerted by the gas. Okay, that being said, let's look at the math. So we know that from all those little simple gas laws, P times V over NT remains always constant. So that whole relationship, we saw that with the general gas law, and when we took all the little gas laws that we saw individually and we put them all together to make the general gas law, or the combined gas law, we saw that this whole relationship remains constant. Now, for an ideal gas, we're going to work with this, but the difference is we're going to give a value to the constant. So at STP, if you replace by the values that we know, pressure is 101.3, volume is 22.4 for 1 mole, and temperature is 0 Celsius or 273 degree Kelvin, we get a value for K, for the constant, of 8.31. Okay. Now the unit's a little messed up because we're multiplying 4 different types of values, so pressure versus volume over mole and temperature, we get a unit that looks like this. So we have kilopascal per liter over mole Kelvin. So you have two choices. Either you learn it by heart or you analyze it every time you do your calculation. You know that the constant comes from pressure, volume, moles, and temperature, so these are the units. Mind you, it's rare you're going to have to write a final answer that involves the constant. So most probably you won't have to write this unit anyways. And I know that when you do your calculations, you don't necessarily write your units, which is fine by me. So you don't have to learn it by heart. So the ideal gas constant, that's the value. And now if we rearrange this with the value of the constant of 8.31, we get the following. PV equals NR with the value of 8.31 T. And don't forget, again, it's a gas law, so the temperature has to be in Kelvin. So it's the PV NRT law. That's what we're going to refer to, the PV NRT law. That's what we're going to call it. So we're going to look at a few examples next. For example number 1, we have a fairly straightforward example or practice problem. So it says, when inflated to their maximum capacity, human lungs contain approximately 4.09 liters. So I'm going to start putting down my information. Okay, so the volume is 4.09 liters of air at a temperature of 37. So the temperature is 37. If we put that in degree Kelvin, we have 310 Kelvin. If I may point out to you, the volume always has to be in liters because of the value of the constant, which is in liters, amongst other things. How many moles of air, so I'm looking for N, contain, how many moles of air do lungs contain if the air pressure is 100 kilopascal? So pressure, 100 kilopascal. Again, your units of pressure always have to be in kilopascal because that's the way this law is designed. So my law is PV equals NRT. I will replace. So I have 100 times 4.09 liters over, and I don't know what it is. Actually, sorry, what I should say is NRT. So N times 8.31, which is the constant, times my temperature of 310 kilopascal. So let me go and, and erase. Not here. Here. Let me go and erase this. So now all I have left to do is to solve for my N over here. So I will do 100 times 4.09 divided by 8.31 and also divided by 310. So that will give me, in the end, 0.159 mole. Now, when you do your calculations, this being a constant, the 8.31 being a constant, it does not count in your significant figures. So if you analyze, you have 3 sig figs here, 3 here, and 3 here. So my answer in moles should have 3 significant figures, and it is the case. So my final answer is 0.159 mole. Now let's move on to the second example. Okay, so here's example number 2, and it says, if 10 grams of methane, CH4, are burned during a combustion at SATP, what volume of methane will have reacted? First thing I need to do, of course, is to convert my mass, so let's do that. So I have a mass of 10 grams of methane. I know that my molar mass is 16.05 grams per mole. So if I calculate my number of moles, that gives me 0.623 and 1 mole. Okay, so here, of course, I used N is equal to M over M. Okay, now they want you to find what the volume is, and they're telling you that this is happening at SATP. In other words, what they want you to do is fill in all the other information using the values of SATP, except for the volume, because clearly you're not working with 1 mole. If you were working with 1 mole, you know what the volume would be. But here, they're changing the moles on you, and they're saying find the equivalent volume if all the rest is really at SATP. So we know that the pressure at SATP is 101.3 kilopascal, and the temperature is 298 or 25 degrees Celsius. So 298 Kelvin, and this is kilopascal. If I use my equation, PV is equal to nRT, and I replace, I get 101.3 times V, I don't know the value, is equal to 0.6231 mole times my constant 8.31 times the temperature of 298. And I get a volume of, let's go and verify, I believe it is 15.2 liters exactly. So the volume, 15.2 liters, if I use a number of moles of 0.6231 mole at SATP. And now let's move on to question number 3, which you don't have in your notes. I just added it because I wanted to give you a different type of example, which involves stoichiometry. I thought you could benefit from that, so you should maybe write it down. That would be a good idea. Okay, so let's go take a look at it. So here it goes. We have, if 2.40 grams of butane, so butane is C4H10. So we have 2.4 grams of butane, mass is equal to 2.40 grams. Reacts in the presence of 14.9 liters of pure oxygen. So I'll put it, you know what, I'll put it over here because I'm talking about a different substance. So volume of oxygen is 14.9 liters at a temperature of 145, which ends up being 418 Kelvin. So 418 Kelvin. What was the pressure? We don't know what that is. Of the oxygen gas. Now I have a problem because I have a mass of C4H10, but all my other values are for oxygen. So I'll need to first find the number of moles of oxygen. And to do that, I need to know how many moles of butane did react. So I'll need to do a little bit of stoichiometry. If you studied with Mr. Rosa, I know you're going to do this differently, so I'll do it my way. And if you don't understand, you can always see me in class. So here, my mass, to go to my number of moles, I'll do 2.40 grams of butane over 58 grams per mole. Now, again, I suggest you keep more decimals so you don't mess it up with the sig figs, but I'll hold on, I'll keep 2 just because it's easier for me to calculate mentally what the molar mass is. That gives me 0.4, no, sorry about that, 0.4138 mole. Now, this is the amount of moles of butane. I need to know how many moles of oxygen I have, so I'll need to do a ratio. My ratio is 2 moles of C4H10 needs 13 moles of O2 to react. Now in this case, I'm not working with 2, I'm working with 0.04138 moles. In that case, how many moles of oxygen would I need or would have reacted? So I'm going to find this value here. So 2 moles of butane for 13 moles of oxygen. But in this particular case, I only have 0.04138. How many moles of oxygen are needed for this amount to react? Well, the amount is 0.26897 mole. So now all I have left to do is solve for P, because I have my volume of oxygen, the temperature at which the oxygen is during the reaction, the number of moles of oxygen involved based on the mass of butane that reacted, and all I need to solve for is P, using PV equals nRT. What I will do is replace, so I don't know P. Actually, what I will do is just say P is equal to 0.26897 times R, which is 8.31, times T, which is 4.18, over V, which has a value of 14.9. And now I can solve for P. The value of P is 63 kilopascal. Now in this case I rounded. Why? Because of my molar mass here. This is what basically determined how many significant figures I would have at the end of the whole problem. So this calculation involves a minimum amount of 2 significant figures. So I would have had 0.41, which would have been translated here or rewritten here. Now these two numbers do not count, they're not measurements, so they don't count in your sig figs. So 0.41, so 2 sig figs, would have given me 2 significant figures here, which would have been rewritten in here as 2 significant figures. My 0.31 doesn't count, it's a constant. So we have 2 sig figs, 3 sig figs, 3 sig figs. My final answer has 2 significant figures. So here you go. You're gonna have plenty of practice. You're gonna have to work on problems like this. This is really the biggest chunk of the chapter 2. So make sure that you really master all possible problems that can be asked, because this is for certain you're gonna get a problem on this at the end of the year, and they always try to kind of catch you or give you a tricky question. So make sure that you master this concept very well. So if you have any questions, you can see me in class. See ya!